All right, guys, let's continue to talk about triangles, and we're going to introduce some special segments today. In order to continue the video, you're going to want to take out your yellow study guide that has the notes organizer on one side and room for questions on the other. Go ahead and take that out. If you need to pause, do so, and then press play. So special segments. We're going to break our chart into 3 columns at a time. First off, talking about the left 3 pertaining to the special segments, following up with the 4, 5, and 6 column on the right, talking about points of concurrency. Here we go. You'll notice that there are 4 types of special segments. Some of those terms should look familiar, okay? And we're going to talk uniquely about each one, and then head to the diagram and see what types of notation you should find in a picture, or you will be able to label in a picture. Starting off with the first one. A perpendicular bisector is a special segment in a triangle, and it's going to do 2 things. First, it's going to bisect the side. What does that look like in the diagram? That means point P is the midpoint of segment AB, and let's add some tick marks there. So first off, a perpendicular bisector will bisect the side. The second thing that it's going to do is create a 90-degree angle of intersection. And again, what might that look like in the diagram? Go ahead and draw that 90-degree angle. Second, let's talk angle bisector. Again, that word bisect, continuing trend, but this time pertaining to angles. So an angle bisector is going to divide an angle, or each angle, into 2 congruent smaller angles. What might that look like in the diagram? Go ahead and give yourself those curves, 1 in each angle. The third type of segment is actually one that you saw in the benchmark, question 12, but you were given the definition because it was a new term. Okay? Let's go ahead and define that at this time. A median is a segment drawn from vertex to the midpoint of the opposite side. Take a look at your picture. If we connect the vertex B to the midpoint of the opposite side, that means point D is the midpoint of segment AC, and we can go ahead and put tick marks on each piece there. AD is congruent to DC. The altitude, our last special segment. The altitude is going to be the height of the triangle. Okay? And what exactly does that mean? It represents the perpendicular distance from vertex to base. Now you'll notice that there are 3 triangles in this picture, and it is unique of the 4. Here, in an acute triangle, the altitude can be inside. Here, for an obtuse triangle, you might find the altitude outside the triangle. And finally, in a right triangle, you might find the altitude to actually be a side of the triangle. So the altitude can be inside, outside, or a side of a type of triangle, and it's going to depend on how you classify the triangle you're working with. Finally, it is the perpendicular distance, so we can say that all of our altitudes are perpendicular to the base. If you need to pause to jot down any final notes or any questions you might have for your teacher, please do so, and then press play again. Let's head to the second half of our table and talk about points of concurrency. You'll notice our 4. Each one of these is probably a brand new word, and that's okay. We have time to work with them. We have circumcenter, incenter, centroid, and orthocenter, all kind of based loosely on the word center. Starting off at the top, let's talk circumcenter. Your circumcenter is created by your perpendicular bisectors. So DP, PE, and FP are all perpendicular bisectors of that triangle. There is a unique property of point P created by the perpendicular bisectors, and that is that it is equidistant from each vertex. Point P, the circumcenter, is equidistant from each vertex. What might that look like in your diagram? These dotted segments that represent the distance from the circumcenter to each vertex are all congruent lengths. So the circumcenter is equidistant from each vertex. Let's go to the next one, the incenter, which is created by your angle bisectors. Okay, so we've bisected angle A, angle C, and angle B to create this point P inside the triangle. What do we know to be true about your incenter? We know that it is perpendicular and equidistant from each side. It is perpendicular and equidistant from each side. So again, what might that look like in your diagram? The dotted segments or dashed segments are not only congruent in length, but are also perpendicular to the side it intersects. Now you'll notice in both of these top pictures, there's a triangle, okay? And I want you to think about the position of those triangles in relation to the name, and ask your teacher about those on Friday. Okay? Think about why those triangles are there, what that might mean. Down to the bottom two, let's talk about centroid created by your medians. So F is a midpoint, E is a midpoint, and D is a midpoint. Medians create the centroid, and the centroid is located at a unique position along the median. Okay? P is 2/3 the length of the median from the vertex. So this part of the median is 2/3 the overall length of the median. Next, P is 1/3 the length from the midpoint. Which means that that point P to F, that represents 1/3 of the overall length of the median. So if our median was 15 units long, B to P would be 10 units, and P to F would be 5 units. We have that 2/3, 1/3 split, and you'll be doing lots of practice with that Friday and Monday coming up in this unit. Finishing it up, orthocenter. The altitudes of a triangle create the orthocenter point, P. Now the unique property of the orthocenter is its position based on the type of triangle that you have. If your triangle is acute, the orthocenter will be inside, and that's what you see pictured in that diagram. If your triangle is obtuse, the orthocenter will actually be positioned outside the triangle. Okay, think about what that might look like. You'll be exploring with some constructions next week. And finally, if you have a right triangle, the position of the orthocenter will be on a side of the right triangle. So it's not inside, it's not outside, it is on a side of that right triangle. So think about your unique properties. Equidistant from each vertex, perpendicular and equidistant from each side, a 2/3, 1/3 relationship here pertaining to length of the median, and then the position or location of the orthocenter in terms of what type of triangle you have. So this paper right here is going to become a key document for Friday's class, Monday's class, Tuesday's class, Wednesday and Thursday also, all leading up to the test. Definitely hold on to this paper, bright yellow, can't lose it. Please make sure that you write down any questions you might have for your teacher, and have a great night.